Hello friends, welcome to ChemShastra. Today we are going to talk about a very important concept from coordination compounds, that is a crystal field theory. Now in crystal field theory, basically what we are going to study is we are going to study a complex formation which is going to happen. Now what is a complex? Basically it is made up of the central metal atom surrounded by the ligand. Okay, there is a coordinate covalent bond between the ligand and the central metal atom in this case. Now, before getting into the actual what crystal field theory information, what kind of information crystal field theory gives you, let's talk about some type of orbitals that we have. Now, in the case of d orbital, your coordination compound basically based on the d block elements. So obviously d block elements will have the d orbitals. In d orbitals, what you are having is there are 5 types of d orbitals. One is dxy, another one is dxz, third one is dyz. Fourth one is dx2 minus y2 and the last one is a dz2 orbital. Now if you will see, when you are talking about dxy orbital, it is an orbital where the lobes are present between the axes, okay, x-axis and the y-axis. When you are talking about dxz orbital, it is the orbital where you are having the lobes present between the x and z axis. When you are talking about a dyz orbital, it is a case where orbital or the lobes are present between the y and z axis. But when you're going to talk about dx2 minus y2 orbital, it is going to be, the orbital is going to be present along the y-axis and the x-axis, and dz2 orbital where the lobe is going to be present along the z-axis. So basically if I want to classify this 5 orbitals into 2 specific classes, which we do in the case of crystal field theory understanding, these are the 3 cases where the orbitals of the lobes are present in between the axes. This set of orbitals in coordination in crystal field theory is called T2G set of orbitals. And this 2 set of orbitals, in this case, having lobes present along the axis. So that's why this set of orbitals are called EG set of orbital in the case of crystal field theory. Now let's talk about what basically is a crystal field theory. In crystal field theory, we take into consideration the electrostatic interaction between the central metal atom and the ligand. That is what we consider. Second thing is we consider them as a one point interacting with another point. Okay. So basically what crystal field theory gives you, or in the case of crystal field theory, we are going to talk about 2 main things. One is we are going to talk about the complexes which are going to form in an octahedral way. Okay. Or the octahedral complexes. Second kind of complexes that we are going to discuss is a tetrahedral complexes. So these are the 2 kinds of complexes that we are going to discuss in the crystal field theory and how the splitting happens when there is a formation of a complex that happens. Okay, so if you'll see any orbital, as I said, in the case of coordination compounds, you will always have the d block element or the transition element present in any complex as a central metal atom. So in that case, as I said, it is a d block element. How many orbitals you have? You are having 1, 2, 3, 4, 5 orbitals. These are the d orbitals. It can be in any sequence, but you can consider this as dxy, dyz, dxz. Then this is dx2 minus y2 and dz2. The same sequence that we have followed in the case of the structure of d orbitals. Okay. Now these 5 d orbitals are initially degenerate when your metal ion or metal atom is in the free state. When your metal ion or atom is in the free state, at that time this all d orbitals are at the same energy level. You can see we have written E over here. This E represents, we are talking about the energy of the orbitals. So in this case, what you are having is you are having metal atoms which are in the free state. So all these 5 d orbitals are at the same energy level. So we call it as they are a degenerate set of orbitals. Now what crystal field theory says is whenever complex formation happens, if initially you have a central metal atom or ion in a free state, then the incoming ligand approaches the central metal atom in a spherical field. Now when you are talking about a spherical field, metal is at the center, ligands are approaching in a spherical way. In that case, every ligand is equidistant to the central metal atom. So what they are saying is, when you are having a complex formation, initially what happens is, initially you are having a central metal atom or ion in the free state. Then in the second step, the ligands are going to approach in a spherical field. No matter whether it is a tetrahedral complex or an octahedral complex, your ligand will approach in a spherical field. Now when you are saying that it is in a spherical field, indirectly we are saying that every ligand is equidistant from the central metal atom. Okay, because of that, what happens is your metal is made up of what? Electrons. Okay, metal is surrounded by electron. You are having a ligand. What is basically ligand? They are coming with their own electron pair. So they will be surrounded by the electrons. So there is an electronic repulsion that happens between the metal and the incoming ligand. Now that because of that repulsion, your d orbitals of the metal goes to the higher energy level. But again, as we have mentioned that your metal is approached by ligand in a spherical field. Now when you are saying your metal is approached by the ligand in a spherical field, in that case all the d orbitals will have the increase in energy to the same extent. That means your energy of the d orbital has gone up in this case, but still they are degenerate. Your dx2 minus y2, dz2, then dx2 minus y2, we already said, dxy, dyz, dxz, all these 5d orbitals will be at the same energy level, but that energy level will be higher than when your metal was in the free state. Now why they are going in the higher in energy? Because of the repulsion that is happening. With the repulsion between the metal atom, central metal atom and the ligand, there will be what? The stability of the complex will decrease, and because of that what will happen? The energy will go up. Okay, the energy level of d orbitals will go up. Okay, what happens further is there is a third step in the crystal field theory where what we say is, based on what you have, whether you have an octahedral complex or a tetrahedral complex, the last step will vary. Okay, now as I said that we are going to classify this three set of orbital as T2G set of orbitals, and these two set of orbitals as a EG set of orbitals. Okay, now in what way they're differing from each other? In this case the orbitals are present in between the axes, and in this case what you have is the orbitals are present along the axes. Okay, so this is the only point of difference between these three set of orbitals and this two set of orbitals, right? Now what happens is, in the case of now we are going to talk about an octahedral complex. In octahedral complex, the now ligand will approach in an octahedral field. Now when the ligand is approaching in an octahedral field, what happens is, in this case the ligand approaches along the axes. What does that mean? Now you are having this as a suppose z axis. Okay, now this ligand, now this is in a one same plane. Okay, this red ligands are in the same plane, and you are having this blue one perpendicular to this red plane, and this blue one is also perpendicular to the red plane, right? So this angle is actually, we cannot show that on the paper, but this angle is actually a 90-degree angle. So this is a z axis, then what you are having is a x axis, right? And what else you are having? Now this one, what you have is a y axis. So if you will see, if you extend all these angles, axes, your ligands are approaching along the axis when you are having an octahedral complex formation, right? Now just tell me one thing. I'm giving you two arbitrary situations. Suppose there are two accidents which are happening. Just I'm giving you as a one analogy to understand. In the case, now this is the best car I can draw. Okay, there's two cars which are approaching in opposite direction. Okay, and they are having a head-on collision. ठीक है, आमने सामने एक दूसरे के टकरा गया. ठीक है. Then there is a second case where there are two cars approaching in the same direction. Okay, in opposite directions, and they are going to have a collision, but it is not a head-on collision, it is a side-by-side collision. Can you tell me in which case the severity of accident will be high? In the case of accident where there is a head-on collision between the two vehicles, in that case the severity will be high. Why? Because it is a head-on collision. When you are going to struck something, or when you are going to hit something with a very high force, surface area बढ़ेगा यहाँ पे, that's why collision will be high. Okay, उसका impact high रहेगा. When you are going to have a side-by collision, obviously impact is going to be there, but the severity will be very less in comparison to the first condition. Okay, now why I'm telling you this? When you are having the two type of orbitals, you are having one type of orbital where your lobes are present in between the axes, and when you are having two set of orbitals where you are having lobes present along the axis, and your ligand is approaching along the axis. So when the ligands are approaching along the axes, in the case of octahedral complexes, the orbitals which are present along the axes will have a very huge impact. Okay, they are going to have head-on collision with the incoming ligand. So what are the orbitals which are present along the axis? Your dx2 minus y2 and dz2 are the orbitals which are present along the axes. So they are going to have the highest collision with the incoming ligand, and that's why they will have the very high repulsion. And because of that, you can see over here your dx2 minus y2 and dz2 in the case of octahedral complexes goes high in energy, right? This is the reason why they goes for high in energy, okay, with comparison to their actual neutral point. Okay, Now this is the EG set of orbitals that you have, okay, in coordination complexes or in your crystal field theory. Now the orbitals which are present in between the axes, as they are not going to have head-on collision, they goes lower in energy, which are like dxy orbital, dyz orbital and dxz orbital, which is basically your T2G set of orbital. Okay, now this central point, which is the initial point of energy, is called barycenter, okay, which is nothing but you can consider where your energy is neutral, okay, or zero at this point. All the orbitals will have the zero energy because it was the initial energy of the complex, or sorry, not complex, metal ion when your ligand is approaching in the spherical field. This is called barycenter. Okay, so if you'll see from this point, your energy goes up for dx2 minus y2 or dz2 orbitals. This energy gap is called 6 dq gap. Okay, this complete energy gap is called 10 dq, or some call it as a delta as well. Okay, and if you are calling it as a 10 dq, then this energy gap is 6 dq and this energy gap is of 4 dq. Okay, if you're calling this as a delta, then this energy gap you can refer to as a 0.4 delta, and this energy gap you can refer to it as a 0.6 delta in this case. Okay, so these are way of representing. Now what is this? This is basically energy gap which we call as a crystal field stabilization energy. So what we are talking about is the energy basically. Okay, so this is a crystal field stabilization energy. Now very simple thing to tell you, if you're going to put the electrons in, now when you are having, what is the Hund's rule? You have to follow the Hund's rule in this case when you're filling up the electrons. When you have a one single electron, there's a no question of where you are going to place the electron. It's very obvious. Okay, the orbital which is having a lower energy, you are going to fill that orbital first, right? Now in this case, what you're going to have is you're going to fill this orbital first, and when you don't have option, you will be filling this orbitals. Now there are again two kinds of complexes: high spin complexes and low spin complexes that we are going to discuss in the different video. But right now, at least you understand this. This is the energy gap. This gap is called crystal field stabilization energy. Okay, so this is a plus 6 dq gap and this is a minus 4 dq or 4 dq gap. You can remember this is a 0.6 delta or this is a 0.4 delta. Now basically, if you're going to put electrons in this lower energy level orbitals, your complex will become very stable. When you're going to put the electrons in this orbitals, your complex will become unstable. Okay, so it's obviously now again that depends what kind of ligand you are having. Based on that, whether you're going to go for the pairing of electrons or maybe you're going to fill the electron singly, that will depend from complex to complex because of mainly ligand, because ligand has everything to do with this, because this energy gap, okay, is completely based on what kind of ligand you have, whether you have a strong field ligand or a weak field ligand. Based on that, this energy gap is decided. Okay, and the general comparison we do it by the 10 dq value. So this is about crystal field theory in the case of octahedral complexes. Okay, so understand this very well, why this is happening, why dx2 minus y2 dz2 is going high in energy, because they are the orbitals which are present along the axes, and in the case of octahedral complexes, your ligand are approaching along the axis, so there's a head-on collision. Because of that, ligand is going in high in energy. Orbitals are going higher in energy in the case of dx2 minus and dz2 orbitals. The orbitals like dxy, dyz and dxz orbitals, in this case the orbitals are present in between the axes, so ligands are not going to have any repulsion with them, and that's why they go lower in energy. This energy gap is called crystal field stabilization energy, which is basically your 10 dq value. This energy gap is of 6 dq and this energy gap is of 4 dq. Now why this is like this, you have to, as I said, this is the initial point, or the original point is called barycenter. It should be maintained at 0. Now just imagine, suppose if you are filling total electrons, how many complete electrons you can fill over here? You are having 3 orbitals, so you can fill 6 electrons in the case of lower dxy, dyz and dxz orbital, or basically your T2G set of orbital. So 6 electrons you are having, 6 multiplied by 4 becomes how much? 24, right? So whatever electrons you are going to put in these orbitals, that will stabilize the complex. That means that will decrease the energy by minus 24 dq. Okay, and whatever, suppose if you are having these orbitals which are completely filled in this case, so again what you're going to have is total, not 6, 6 electrons you can put over here, right? In this case, total how many electrons you can put? You can put 4 electrons. So if you're going to put electron in the higher energy orbitals, you are going to have what? Destabilization of the complex. So it will be positive energy will be added in the complex, which will destabilize the molecule or the complex ion or the complex compound. So how many maximum electrons you can put? You are having 2 orbitals, so you can put maximum 4 electrons. 4 multiplied by the value is 6 dq in this case, so that becomes 6 dq, which is nothing but plus 24 dq. So if you are going to fill all the electrons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the complex, obviously if the central metal atom is having that electron, in that case what you're going to have is minus 24 dq plus 24 dq, which will make a barycenter is equal to 0. So basically that's the way how this is distributed, why this is a 6 dq gap and why this is a 4 dq gap. Okay, I hope this makes the octahedral complexes a very clear stuff. Let's move on to the next part, which is again a part of your coordination complex, and basically we are going to talk about the crystal field theory only. In this case, we are going to talk about the molecule or the crystal field theory in terms of tetrahedral complexes. It works on a bit different way, but not that much of difference. Again, the same logic, you are having a central metal atom or ion which is in the free state when your ligand is not approaching the metal. Okay, all your d orbitals like dx2 minus y2, your dz2 orbital, your dxy orbital, dxz orbital and dyz orbitals are degenerate. That means they are at the same energy level. Okay, when your metal atom or ion is getting approached in a spherical field. So these two steps are very common to the octahedral complexes as well as to the tetrahedral complexes. So when they are going to get approached in a spherical field by the ligand, the orbitals will go higher in energy in a comparison to when your metal was in the free state, but still they will be degenerate. You are going to have dx2 minus y2 orbital, in this case dz2 orbital, you are going to have dxy orbital, dyz orbital and dxz orbital. You write it in any sequence, doesn't matter, because still they are degenerate orbital. Now what happens next is a very interesting stuff. Now in this case you can see we are talking about a tetrahedral complex. Now what is a tetrahedral? Basically एक cube निकाल के उसके alternate points if you are going to select, and if you are going to take the central point of a cube, that will be the point where metal will be present, and the alternate points of the cube represents the tetrahedral ka vertices or the points. Okay, so in this case you can see you are having x-axis, you are having y-axis and you are having z-axis. None of the ligand is present along the axes. Okay, so in this case your ligands are approaching in between the axes. So again the same stuff, you are having 5 d orbitals. Out of that, these 3 orbitals dxy, dyz and dxz orbitals are the orbitals which are present in between the axes, which are T2G set of orbitals. dx2 minus y2 and dz2 orbitals are the orbitals which are present along the axes, which is the EG set of orbitals. Okay, so now the situation has become ulta. Okay, in octahedral complexes your ligands were approaching along the axes. Now in the case of tetrahedral complexes, your ligands are approaching in between the axes. So obviously now the head-on collision, the orbitals which are present in between the axes will have the head-on collision. Why? Because your ligands are also coming from in between the axes. Okay, so in this case actually your dxy, dxz and dyz orbitals will go up in energy. Why? Because they are going to have head-on collision with the incoming ligand. And your dx2 minus y2 and dz2 set of orbitals will go lower in energy as they are not going to have any head-on collision with the incoming ligand. The same stuff, this central point is called barycenter, where your energy should be 0 for the complete orbitals or the complete complex, right? This is the EG set of orbital and this is a T2G set of orbital, right? Again, this energy gap is of minus 6 dq. So if you're going to put the electrons in this orbitals, okay, in that case it will lower the energy of the complex, which will stabilize the molecule. This energy gap is of a plus 4 dq. That means energy will be added or increased if you're going to put the electrons in this set of orbitals, right? So that will destabilize the molecule further. Again the same logic you can apply over here. Why this is a 6 and 4 ka gap? The reason being, maximum how many electrons you can put over here? 4 electrons. 1, 2, 3, 4. In each orbital you can put 2 electrons. So 2 2s are 4, that is makes it 4. So minus 4 into what is the energy gap? It's a 6 minus 4 6 dq. Okay, so which makes it to be minus 24 dq, right? How many electrons you can put it over here? 1 2 3 4 5 6. So 6 plus 6 into 4 dq, which makes it to be plus 24 dq. So if you do the complete addition in the when your all the orbitals are having the electrons occupied, minus 24 dq plus 24 dq, which will make out to be 0. Okay, so your barycenter will be the 0 center. Okay, this energy gap is complete energy gap, which is called basically your 10 dq value, which is your crystal field stabilization energy. Okay, I hope this is a very simple stuff. Okay, crystal field theory जितना difficult समझते हो उतना है नहीं. Okay, provided you know what is the geometry of your d orbitals and what is the logic behind crystal field theory in the case of octahedral complexes, and what is the difference in the case of tetrahedral complexes. Just to summarize, I'm giving you again the same, I'm just explaining the one thing in a very clear way. In a case of octahedral complexes, you are having ligands are approaching along the axis, and that's why the orbitals which are present along the axes are having a very strong impact and they are going higher in energy when the splitting is happening. Okay. In the case of tetrahedral complexes, if you talk about your ligands, now you can see over here, I have drawn already the diagram. In this case, your none of the ligand is coming along the axis. Your all the ligands are coming in between the axes. So the orbitals which are present like dxy, dyz and dxz and dyz, these are the orbitals where lobes are present in between the axis. So they will have the head-on collision, and that's why they go higher in energy in a comparison to dx2 minus y2 and dz2, which is nothing but your EG set of orbitals. Okay, so same splitting se ulta likho. Okay, now again I am mentioning this one thing in a very clear way. This splitting gap is completely dependent on the nature of ligand, whether you have a weak field ligand or whether you have a strong field ligand. Based on that, we decide whether you are going to go for a highest possible pairing or whether you are going to put the electrons singly first. Okay, that we are going to discuss when we are going to discuss the magnetic properties with the help of crystal field theory. I hope this makes everything clear about a crystal field theory. But still, if you have any doubt on crystal field theory as such, you can put that in the comment box below. I'm so sorry, not below. Okay, so you can put that in the comment box below. And what you can do is, if you still have any doubt, you can put that on my mail ID as well, ChemShastra@gmail.com. I'm here to help you. I'm here to give you all the knowledge that I have. Okay, so stay tuned. Do subscribe to ChemShastra. जितना वीडियोस अपलोड ऑलरेडी हो चुका है सब देख लो, लाइक करो, शेयर करो, वापस देखो, बार बार देखो. कंसेप्ट जितने बार अच्छे से समझोगे उतना बाद में जाके डिफिकल्टी कम होगा. ओके, एंड इफ यू स्टिल हैव एनी डाउट, अगेन आई एम मेंशनिंग दैट, पुट दैट इन द कमेंट बॉक्स बिलो. ओके, चलो अपने फ्रेंड्स के साथ भी शेयर करो, नॉलेज बांटने से बढ़ता है. ओके, सो बाय बाय एंड टेक केयर.